Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered if the numbers reported in science papers are always true or if there is a way to check if they're accurate? Well, this fascinating new research might have some answers for us. Researchers have found that the numbers we see in science papers aren't always independent. Things like the sample size, the average score, and the possible range of a measurement all put limits on what the standard deviation can be. If a reported standard deviation falls outside these limits, it signals an error or something worse. The cool part is that you don't need the original data to spot these impossible numbers, just what is printed in the article. This study dives deep into these mathematical boundaries, showing how they can be used to check the trustworthiness of research. Think about it like this. If you are measuring how happy people are on a scale from 1 to 7, your average happiness score can be a 10, right? It has to be somewhere between 1 and 7. Similarly, the spread of those scores, measured by the standard deviation, also has limits based on the sample size, the average score, and that scale's range. This paper explains that a standard deviation that is too big or too small for the given information is a red flag. It is like finding a puzzle piece that just doesn't fit, no matter how you try to force it. The researchers have put together a really neat way to understand all these different constraints. They're like Russian nesting dolls, where each new piece of information like the sample size or the mean score, or even if the data must be whole numbers, makes the possible range for the standard deviation even smaller. This step-by-step approach helps clarify which constraints are most important and how they build on each other. The history of these ideas goes back a long way, even to 1918. Mathematicians were already figuring out how to set boundaries for variances. Then, in 1935, Popoviciu came up with a sharp upper bound, which is really important for understanding the maximum possible spread of data. What is amazing is how many times these same ideas have been rediscovered independently by different people in different fields, like statistics, sociology, and even psychology. It really shows how fundamental these mathematical relationships are. One key development was understanding how the average score, or the mean, affects the possible standard deviation, Muilwijk, and later Bhatia and Davis showed that if the average score is very close to the minimum or maximum of the scale, the standard deviation must be smaller. It makes intuitive sense if everyone scores around the 1 on a 1 to -7 scale. There can be a lot of variation in their scores. This bound is like a curved ceiling that lowers as the mean gets closer to the ends of the scale. When dealing with data that must be whole numbers, like Likert scale responses, things get a bit more complicated. The researchers introduce a concept they call quasi-integer data. This means that almost all the data points are integers, but one can be a fraction. This relaxation is important because it allows the bounds to be continuous curves, making them easier to work with and ensuring that the checks don't accidentally flag valid data due to rounding. It is a clever mathematical trick to keep the system working smoothly. This section gets into the nitty-gritty of the lower bound for standard deviation when you have quasi-integer data. It is a bit of a mouthful, but the key takeaway is that for the first time in this series of constraints, the minimum standard deviation can actually rise above 0. This happens because if your average score isn't a perfect whole number, you can't have all your data points be exactly the same. Even a little bit of variation becomes mandatory, pushing the minimum standard deviation up. Now, things get even more interesting when we consider composite scores, like when you add up the scores from several survey questions to get a total score. The reported Cronbach's alpha, which measures how well those items hang together, puts another constraint on the possible standard deviation of the composite score. This is a novel contribution of this paper. A higher Cronbach's alpha means the items are more consistent, which in turn limits how much the composite score can vary. It is like a second layer of rules for the spread of the data. This formula shows how Cronbach's alpha can actually increase the minimum possible standard deviation for a composite score. This might sound counterintuitive, but it is because a high alpha implies that the items are measuring something very similar. If the items are too similar, you can't have a composite score with a super low standard deviation. Especially at whole number means, it means a certain amount of variation is actually required to achieve that high level of internal consistency. The researchers also explore what happens when you only consider that the data must be integers without knowing the range or the mean. They find that the maximum standard deviation for data spanning just one unit, like going from 3 to 4, is bounded by a couple of constants. This is really useful because it gives us a universal check on standard deviation, regardless of the specific scale used, as long as the data are integers. This table is a fantastic summary of everything they've worked out. It shows how each added constraint scale limits, sample size, mean, integer data, and Cronbach's alpha progressively narrows down the possible range for the standard deviation. You can see how the mathematical complexity increases, but so does the power of the check. This table really brings the concepts to life. It shows how many possible combinations of mean and standard deviation are ruled out as more constraints are added. What is striking is how much work the sample size and the mean do in eliminating impossible values, and then how imposing integer constraints dramatically reduces the possibilities. The addition of Cronbach's alpha further refines these possibilities, though its impact is less dramatic than the integer constraint in this specific example. This figure is a visual feast of the entire framework. As you move down the rows, you see the possible region for the standard deviation shrinking with each added constraint. The columns show how this changes for different sample sizes and numbers of items. It perfectly illustrates how the mathematical boundaries become tighter and tighter, making it easier to spot inconsistencies. The distinct patterns for single items versus summed items and the effect of Cronbach's alpha are clearly displayed. One of the most practical parts of this research is the acknowledgement that reported numbers are almost always rounded. This means that a reported mean of, say, 2.97 actually represents a small range of possible exact means. The researchers stress that any trustworthiness check needs to account for this rounding. Otherwise, you might wrongly flag a real dataset as impossible. Their software implementation explicitly handles this, which is crucial for real-world applications. It is super important to understand that these bounds are just that, bounds. If a reported standard deviation falls within these limits, it doesn't automatically mean the data is perfect or even possible. It just means it hasn't violated these specific mathematical rules. The paper emphasizes that these bounds rule out impossible values, but they don't rule in possible ones. Think of it like this: if a number is outside the bounds, it is definitely wrong, but if it is inside the bounds, it might still be wrong for reasons not covered by these specific checks. Like if the data isn't truly integer or if the reported alpha isn't accurate. When it comes to multi-item scales and their reported Cronbach's alpha, the researchers highlight 3 zones. Zone 1 is impossible no matter what. Zone 2 is impossible given the reported alpha, meaning the alpha is inconsistent with the reported mean and standard deviation. Zone 3 is consistent. This provides a clear framework for assessing the reliability of reported statistics, especially for composite scores. They even suggest that if an alpha isn't reported, you can use a reasonable default value to conduct a conservative check. So what does all this mean for us as consumers of scientific information? These researchers have essentially created a powerful toolkit for checking the integrity of reported statistics. They've unified nearly a century of scattered mathematical work into a practical framework. By understanding these bounds, we can become more critical readers of research. We can spot potential errors or even more serious issues that might otherwise go unnoticed. The fact that these checks can be done with just the reported numbers is incredibly valuable, especially when the underlying data isn't shared. In my opinion, this research is brilliant because it takes complex mathematical ideas and turns them into actionable tools for science consumers. It is like giving us a set of detective glasses to look at research papers. The biggest strength here is the historical review and the unification of all these rediscovered findings. It is a monumental effort to bring order to a fractured literature. They've also done a fantastic job of explaining very technical concepts in relatively simple terms, though some of the math does get quite dense. The limitations, as they rightly point out, are that these bounds are not definitive proof of correctness. A number within the bounds might still be faked or erroneous in ways not captured by these specific constraints. Also, the alpha. Base bounds are stated as valid rather than sharp, meaning there is a wider margin of safety, and a pass doesn't guarantee attainability. Future research could focus on developing even tighter bounds, perhaps incorporating more sophisticated statistical measures, or applying these checks to a wider range of scientific disciplines to see how prevalent these inconsistencies are. Ultimately, this work empowers us to be more discerning about the scientific information we encounter. It's a call for greater transparency and accuracy in reporting research. What do you think about these mathematical checks for science papers? Are there any other aspects of research reporting that you find confusing or that you'd like us to explore? Let us know in the comments below, and if you found this video helpful, please give it a thumbs up, subscribe to RUBIN'S Mind Lab for more science breakdowns, and hit that notification bell so you don't miss our next episode. Thanks for watching, and we'll see you in the next one.